The F-100 Super Saber made history on May 25, 1953, becoming the first United States Air Force fighter to achieve supersonic speed in level flight, with a maximum speed of 924 mph and a service ceiling of 50,000 feet. This revolutionary aircraft represented a significant leap in aviation technology between 1953 and 1959. North American Aviation produced 2,294 of these remarkable fighters. The F-100D Super Saber, the most widely produced variant, showcased significant engineering advancements, notably its extensive use of titanium in the airframe and improved avionics systems. During the Vietnam War, these first supersonic fighters proved their combat capability by flying 360,283 sorties and delivering over 30 million pounds of bombs. However, this groundbreaking achievement came at a cost, with the aircraft experiencing significant operational challenges that would influence future fighter designs. This video will explore the revolutionary engineering behind the F-100 Super Saber, from its innovative aerodynamic design to its powerful propulsion system, and examine how its development shaped modern military aviation. Breaking the sound barrier, the F-100 Super Saber's genesis. In January 1951, North American Aviation approached the U.S. Air Force with an ambitious proposal for a supersonic day fighter dubbed the Saber 45. This initiative came just 4 years after Chuck Yeager's historic sound barrier breakthrough in the Bell's -1, marking the beginning of a new era in military aviation. Initially, North American Aviation envisioned the F-100 as a superior successor to their successful F-86 Saber fighter. The company's proposal led to an official order for 2 prototypes on January 3, 1952. The aircraft was designed with a revolutionary 45-degree wing sweep, notably different from the F-86's 35-degree configuration. Furthermore, the design featured a distinctive nose intake that tapered into a flattened elliptical shape, setting it apart from its predecessors. The quest for achieving supersonic flight in the 1950s presented engineers with unprecedented challenges, each requiring groundbreaking innovations to overcome. At the heart of these efforts was the development of the F-100 Super Saber, a fighter aircraft that set new standards in speed and performance. An engineering marvel equipped with an advanced afterburner system. The afterburner design played a critical role, injecting raw fuel directly into the engine's tailpipe to produce a dramatic surge in thrust. This system enabled the F-100 to reach speeds up to 850 miles per hour at high altitudes, with the potential to break through the sound barrier under controlled conditions. In addition to the revolutionary propulsion system, the F-100's 45-degree swept wings represented a significant aerodynamic innovation. These sharply angled wings reduced drag at high speeds, allowing the aircraft to maintain stability and control while approaching and exceeding Mach 1. Specialized fuel management systems further enhanced the Super Saber's ability to sustain supersonic operations by ensuring efficient fuel delivery under the immense stresses of high-speed flight. These efforts culminated during the maiden flight of the YF-100, a prototype which achieved Mach 1.05, officially breaking the sound barrier and demonstrating the feasibility of sustained supersonic flight. This milestone marked a transformative moment in aviation history, proving that cutting-edge engineering and daring innovation could push the boundaries of what was once thought impossible. The technologies developed for the F-100 would not only secure its place as the world's first operational supersonic fighter, but also lay the groundwork for subsequent advancements in high-speed military aviation. Despite its groundbreaking achievements, the journey to supersonic excellence for the F-100 was fraught with significant challenges. Among the most pressing were critical stability issues that posed serious risks to pilots and operations. Directional stability proved to be a persistent problem, with the aircraft often experiencing unrecoverable yaw and roll during flight. This instability was further compounded by a phenomenon known as the saber dance, caused by wingtip stalling, which could lead to sudden loss of control during low-speed maneuvers, particularly during takeoff or landing. Additionally, the F-100 struggled with inertia coupling, a dangerous condition that occurred at high angles of attack, where the aircraft's rotational forces overwhelmed its aerodynamic controls. These challenges resulted in 6 major accidents by November 1954. Consequently, the most devastating incident occurred on October 12, 1954, when North America's chief test pilot, George Welch, lost his life during a dive test of an early production F-100A. The accident investigation revealed that the undersized tail was the primary culprit, causing unstable flight characteristics and uncontrollable yaw. Despite these setbacks, the pressing need for advanced fighters, coupled with development difficulties in other programs like the Republic F-8 Thunder Streak, prompted the Air Force to move forward with the F-100A's deployment. This decision would lead to significant modifications and improvements in subsequent variants. Revolutionary aerodynamic innovations. Engineering excellence in the F-100 Super Saber manifested through 3 major aerodynamic innovations that set new standards in military aviation design. The Super Saber's distinctive 45-degree wing sweep marked a significant advancement in aerodynamic design. This configuration, specifically engineered for supersonic flight, represented a notable increase from the F-86's 35-degree sweep. The wings of the F-100 Super Saber were designed with several innovative features that significantly enhanced its performance and handling. Ailerons were strategically mounted inboard to improve the aircraft's rolling capability, allowing for greater precision and responsiveness during high-speed maneuvers. The wing design also featured a thinner airfoil profile, which reduced drag and contributed to the aircraft's ability to achieve supersonic speeds. Additionally, the wings were constructed using specialized techniques to minimize twisting and bending, ensuring structural integrity and stability under the intense aerodynamic forces encountered during flight. The F-100C variant further enhanced these capabilities with lengthened and strengthened wings, enabling it to carry up to 6,000 pounds of weapons on 6 pylons. One of the F-100's most pioneering features was its incorporation of a stabilator system, making it one of the first aircraft to utilize an all-moving tailplane. This system introduced innovative engineering solutions to enhance flight control and stability. Specialized gearing mechanisms were connected directly to the control stick, ensuring precise input transmission and improved responsiveness. A variable stiffness spring system was integrated to adapt the controls to varying flight conditions, providing pilots with greater control at both high and low speeds. Additionally, advanced resistance controls were implemented to mitigate the risk of pilot-induced oscillation, a critical feature that improved safety and handling during dynamic maneuvers. These modifications proved essential in addressing the aircraft's initial handling difficulties, specifically the dangerous yaw instability that plagued early models. The F-100 Super Saber made aviation history by becoming the first aircraft to extensively incorporate titanium into its airframe. This groundbreaking use of the material provided several critical advantages that transformed its performance. Titanium enhanced the aircraft's structural integrity, allowing it to withstand the intense stresses encountered at supersonic speeds. Its superior heat resistance proved invaluable for high-speed operations, where temperatures could rise dramatically. Additionally, titanium offered exceptional strength while significantly reducing weight, enabling the F-100 to achieve greater speed and maneuverability without compromising durability. Additionally, the airframe featured a semi-monocoque design with stressed skin construction, complemented by a climate-controlled and pressurized cockpit. The F-100D model further refined these innovations through enlarged tail and wing structures. The vertical stabilizer underwent significant modifications to address stability issues. Engineers increased the vertical tail area by 27% and implemented a larger, wider square protrusion that housed advanced radar warning systems. These modifications, along with the reshaping of vertical tail surfaces and rudder improvements, established new benchmarks in supersonic aircraft design. The heart of the beast, J57 engine evolution. The J57 engine represented a revolutionary advancement in jet propulsion technology. Primarily developed in the early 1950s, this powerplant introduced the world's first two-spool turbojet engine design. The innovative dual-rotor axial flow compressor significantly enhanced engine efficiency across various operating conditions. The J57 engine introduced several key innovations that redefined jet propulsion technology. Its dual-spool configuration featured separate high and low-pressure systems, allowing for greater efficiency and performance across a wide range of operating conditions. The engine also achieved an enhanced overall pressure ratio, significantly improving fuel efficiency and making it more effective for sustained high-speed flight. An advanced combustion chamber design optimized fuel-air mixing for more reliable and powerful thrust generation. Additionally, a sophisticated turbine cooling system ensured the engine could endure the intense heat generated during supersonic operations, further solidifying its role as a cornerstone of the F-100's groundbreaking performance. The F-100's J57-7 turbojet engine featured an innovative afterburner system that injected raw fuel directly into the tailpipe, bypassing the jet turbine. This breakthrough design allowed the aircraft to reach impressive speeds of up to 850 miles per hour at high altitudes. In the F-100C variant, an upgraded J57-1A engine was introduced, increasing thrust output and pushing the top speed to 924 miles per hour. The J57-7 delivered 15,000 pounds of thrust with the afterburner engaged, while the J57-1A enhanced performance further, providing 16,000 pounds of thrust. The J57 engine featured a sophisticated control architecture designed to ensure precise and reliable operation. A hydromechanical fuel control system managed fuel delivery to the primary combustion chambers, optimizing performance during standard operations. A separate HMFC was dedicated to regulating the afterburner, ensuring seamless transitions and efficient fuel usage during high-thrust conditions. Additionally, the engine included dedicated NTIs and ignition control systems to maintain functionality and safety across a wide range of environmental conditions. Indeed, the engine's reliability and performance led to its selection for numerous military aircraft, beyond the F-100, including the Boeing -52 bomber and Convair F-100 Delta Dagger. Solving the stability crisis, stability issues emerged as the most critical challenge in the F-100 Super Saber's development, leading to multiple fatal accidents and a complete fleet grounding. By November 1954, the F-100's most dangerous characteristic was its susceptibility to inertia coupling, a phenomenon where the aircraft would experience simultaneous, uncontrollable movement across multiple axes. This condition occurred so rapidly that pilots had virtually no time to correct it before the airframe would begin to disintegrate. Accordingly, the issue claimed several lives, most notably North America's chief test pilot, George Welch, during dive testing of an early F-100A. The issue originated from a combination of three key factors. First, the concentration of mass within the fuselage created imbalances that complicated stability and maneuverability. Second, the gyroscopic effects produced by the powerful turbojet engine added to the aircraft's handling challenges. Finally, the control surfaces were not sufficiently effective to counteract these forces, making it difficult to maintain precise control during high-speed or dynamic flight conditions. In response to these critical issues, engineers developed a solution in the form of a yaw damper system, which was first installed on the 146th F-100C aircraft. The system proved highly effective, leading to its retroactive installation on earlier models. Each unit of the yaw damper system came at a cost of approximately $10,000. Similarly, a pitch damper was introduced on the 301st F-100C, also priced at $10,000 per unit. Structural improvements primarily focused on the vertical tail section. Engineers increased the vertical tail area by 27%, which effectively delayed the onset of instability to speeds above Mach 1.4. Moreover, the aspect ratio of the vertical tail underwent modifications to enhance directional stability. The F-100D variant introduced several refinements to improve its performance and handling. The tail was made larger, with both its height and chord increased to enhance stability. The rudder was also enlarged to provide better control, especially at higher speeds. Additionally, the artificial field systems for the aileron and stabilizer controls were modified, offering more precise feedback to the pilot and improving overall handling during flight. Although these modifications markedly improved the aircraft's handling characteristics, the F-100 maintained a concerning accident rate. Throughout its service life, more than 889 aircraft were lost in accidents out of 2,294 built. Ultimately, these experiences provided valuable lessons for future fighter designs, establishing new standards for stability control systems in high-performance aircraft. Combat systems integration. The F-100 Super Saber's combat capabilities expanded dramatically through its operational lifetime, transforming from a dedicated air superiority fighter into a versatile multi-role combat aircraft. The F-100D Super Saber was a versatile and powerful fighter aircraft with an impressive weapons payload capacity of up to 7,040 pounds, distributed across 6 underwing pylons. This capability allowed the F-100D to carry a wide variety of munitions, making it highly adaptable for different combat scenarios. Its primary armament consisted of Firmina's 39 20mm cannons, which provided a solid foundation for close air support and dogfighting engagements. The aircraft's weapon systems were designed to deliver both precision and destructive power. In addition to the Firmina's 39 cannons, the F-100D was equipped with the ability to carry a range of missiles, including the GAM-838 bullpup and the Firmina's 8 Sidewinder, offering both guided precision strikes and air-to-air capabilities. The aircraft was also configured for nuclear weapons delivery, showcasing its strategic importance during the Cold War. Its nuclear weapons capability was enhanced by the inclusion of the low-altitude bombing system, which allowed pilots to conduct specialized maneuvers like toss bombing, enabling them to release bombs at low altitudes while pulling away sharply to avoid retaliation. Being its nuclear payload, the F-100D carried a broad assortment of conventional ordnance, including napalm canisters and two 75-inch Sunni rockets, which provided additional flexibility for a wide range of ground attack missions. This combination of firepower, versatility, and cutting-edge weapon systems made the F-100D a formidable presence in the skies, capable of executing precise strikes against a variety of targets, from enemy aircraft to ground-based installations. The F-100F variant undeniably marked a milestone as the first U.S. Air Force fighter dedicated to electronic warfare through the Wild Weaselite program. These specialized aircraft were equipped with advanced electronic warfare technology to enhance their operational effectiveness. Among the key components was the undivided by Firmina's 25 radar homing and warning receiver, which provided vector radar capabilities for detecting and tracking enemy radar systems. The aircraft also featured the F-133 panoramic receivers, offering an extended detection range to identify and counter various electronic threats. Additionally, Camini 60 panoramic cameras were installed, enabling the aircraft to capture high-resolution imagery for reconnaissance and intelligence gathering. These modifications enabled crews to detect and locate enemy air defense sites, simultaneously tracking multiple radar types. The Wild Weasel missions primarily involved low-level flying, typically lasting for 2 to 6 hours, with multiple in-flight refueling operations. The F-100D incorporated substantial navigation enhancements, fundamentally improving its combat effectiveness. The Minneapolis Honeywell Menace 3 automatic pilot system allowed pilots to focus on mission-critical tasks, while the aircraft maintained stable flight. In 1966, the Combat Skyspot program introduced X-band radar transmitters, essentially enabling precision ground-directed bombing in adverse weather conditions. This system operated through a network of ground-based and divided by Mach-77 radar stations that tracked strike aircraft and provided precise targeting data. The navigation suite of the aircraft was designed to support a wide range of mission profiles simultaneously, making it highly versatile and effective across various operational scenarios. It facilitated low-level strike operations, allowing the aircraft to conduct precision strikes at minimal altitudes. The system also provided all-weather bombing capabilities, ensuring that the aircraft could perform bombing missions under any environmental conditions. Additionally, the suite enabled the accurate delivery of precision-guided weapons, ensuring high effectiveness in targeting specific objectives. Furthermore, it supported electronic countermeasure missions, enhancing the aircraft's ability to disrupt enemy radar and communications systems. These improvements proved crucial in Vietnam, where F-100D Super Sabers flew their first combat strike on June 9, 1964, against targets in the Plains Deschutes, Laos. Following the Gulf of Tonkin incident, the aircraft undertook both MiG patrols and fighter-bomber strikes over North Vietnam. F-100D Super Saber, the ultimate evolution, representing the pinnacle of North American aviation's engineering prowess. The F-100D Super Saber emerged as the most extensively produced variant, with 1,274 units manufactured. This definitive model marked a substantial leap forward in fighter-bomber capabilities. The F-100D Super Saber underwent several crucial structural enhancements that significantly improved its combat effectiveness and overall performance. Engineers focused on optimizing the aircraft's aerodynamics and durability, making it more capable of handling the stresses of high-speed and combat flight. One of the key modifications was the expansion of the wing root chord, which increased the total wing area to 418 square feet. This change not only improved the aircraft's lift and maneuverability, but also contributed to greater stability at higher speeds. In addition to this, the aircraft incorporated several distinctive design elements. The landing flaps were modified to feature a crankwing trailing edge configuration, which improved aerodynamic efficiency during takeoff and landing. The wingspan was extended by 26 inches, enhancing the aircraft's overall performance during combat maneuvers and contributing to better control at lower speeds. Furthermore, the vertical tail area was enlarged by 27%, increasing stability and control, especially during high-speed flight and in turbulent conditions. Recognizing the importance of durability for long-term service, the F-100D airframe underwent reinforcement programs in 1967. This initiative was aimed at extending the aircraft service life from 3,000 to 7,000 flying hours, ensuring that it could remain in operation for much longer. To address structural concerns, particularly after incidents of wing failure, External bracing strips were added to further strengthen the wings and reduce the risk of catastrophic structural issues. These structural enhancements not only extended the F-100D's operational lifespan, but also made it a more reliable and robust platform for a wide range of combat missions. The F-100D Super Saber was equipped with advanced avionics systems that significantly enhanced its operational capabilities and effectiveness during combat missions. Among the key systems was the undivided by AJB-1B, which played a crucial role in low-altitude bombing operations, allowing the aircraft to carry out precision strikes at reduced altitudes with greater accuracy. The undivided by airframe radar homing and warning system provided the F-100D with the ability to detect and respond to enemy radar signals, enhancing its survivability and ability to counter threats in hostile environments. Additionally, the aircraft featured the Ministry Autopilot, which enabled hands-free navigation, allowing the pilot to focus on other critical tasks during long missions or when engaging with targets. Essentially, the Combat Sky Spy program in 1966 equipped select F-100Ds with X-band radar transmitters, enabling ground-directed bombing operations in adverse weather conditions. The constant speed inverter, primarily responsible for electrical system reliability, required its dedicated oil system due to frequent malfunctions. Project Highwire was a large-scale standardization effort aimed at enhancing the capabilities of the F-100D Super Saber, with modifications made to approximately 700 aircraft, completed in 1965 for $150 million. This extensive program introduced several key upgrades to improve the aircraft's operational range and combat effectiveness. Among the modifications was the installation of 50-gallon air refueling drop tanks, which allowed for extended flight durations and increased mission flexibility. In addition, an in-flight refueling probe extension was added, facilitating the refueling of the aircraft in mid-air and extending its operational reach even further. The project also included the integration of AIM-9BS Sidewinder missile capability, giving the F-100D enhanced air-to-air combat potential. Finally, a true airspeed indicator was installed, providing the pilot with more accurate speed readings during various phases of flight. The aircraft's combat systems received substantial upgrades, enabling it to carry diverse weaponry on 6 hardpoints. In 1959, 65 aircraft were modified to launch the -12 bullpup air-to-ground missile. Straight away, these enhancements established the F-100D as a versatile platform, capable of delivering both conventional and nuclear ordnance. Generally, the F-100D demonstrated remarkable adaptability throughout its service life. An innovative zero-length launch capability was successfully tested on March 26, 1958, utilizing an Astrodyne booster rocket generating 150,000 pounds of thrust. This advancement exemplified the continuous evolution of the Super Saber's capabilities. Engineering lessons learned. Development challenges of the F-100 Super Saber provided crucial engineering insights that shaped future aircraft design. The rapid transition from concept to production revealed fundamental lessons about supersonic flight development. The Air Force's initial assumption that the F-100 represented merely an evolutionary change proved incorrect. Essentially, the Air Research and Development Center recognized this aircraft as a revolutionary leap into unknown territory. North American aviation engineers expressed early concerns about numerous untested characteristics. The development process of the F-100D revealed several critical oversights that affected its initial performance. One of the key issues was the insufficient testing before the aircraft's deployment, which left certain flaws undetected until after it entered operational service. Additionally, the complexity of supersonic flight was underestimated, with many of the challenges and limitations of high-speed flight not fully understood at the time. The aircraft's aerodynamics, particularly at supersonic speeds, were more intricate than initially anticipated, and this lack of understanding led to difficulties in handling and stability. Furthermore, the premature operational deployment of the F-100D meant that it was not fully prepared for the rigorous demands of combat, which highlighted the need for more extensive testing and refinement before widespread use. The F-100's safety record necessitated extensive modifications throughout its service life. The aircraft experienced a notably high accident rate, with 889 aircraft lost out of 2,294 produced. This concerning statistic prompted the initiation of several improvement programs aimed at addressing the F-100D's operational challenges. One key enhancement was the installation of a yaw damper system, which was first implemented on the 146th F-100C to improve stability and control. Following this, a pitch damper was introduced to the 301st F-100C, further enhancing the aircraft's handling characteristics. In response to structural failures, wing bracing strips were added to reinforce the aircraft's wings and prevent further incidents. Additionally, a service life extension program was launched in 1967, significantly increasing the F-100D's flying hours from 3,000 to 7,000, ensuring its continued reliability and operational readiness for years to come. Project Highwire emerged as a comprehensive solution to standardize approximately 700 F-100Ds. Primarily, this program addressed the diversity of capabilities between individual aircraft that had created maintenance challenges by 1,965. The development of the F-100 Super Saber had a profound impact on the evolution of modern fighter design, setting important precedents for future aircraft development. One of the key contributions was the emphasis on comprehensive testing requirements, which led to the establishment of extended prototype evaluation periods. This approach enabled a more thorough assessment of flight characteristics and allowed engineers to investigate stability issues in detail before moving into full-scale production. Another significant shift was the adoption of a systems integration approach, which prioritized standardized modification programs across the fleet. This not only streamlined upgrades and repairs, but also introduced unified maintenance procedures, ensuring greater consistency and efficiency in the aircraft's upkeep. Additionally, the F-100 program highlighted the importance of consistent configuration management, which became a standard practice for ensuring uniformity and reliability throughout the aircraft's operational life. The aircraft's experience with titanium integration proved particularly significant, as it became one of the first American aircraft to utilize substantial amounts of this material in its structure. Otherwise, the constant speed drives reliability issues led to the development of independent oil systems for critical components. The F-100's legacy ultimately influenced the development of subsequent Century Series fighters. Rather than rushing new designs into service, future programs emphasized thorough testing and validation. The aircraft's challenges with yaw instability and inertia coupling established new standards for stability control systems in high-performance aircraft. These lessons proved especially valuable as the Air Force transitioned to more advanced fighters. The F-100's operational history demonstrated the importance of standardization, evidently influencing the development of the F- for Phantom II and F-105 Thunderchief. Formerly accepted practices regarding rapid deployment were replaced by more rigorous evaluation protocols. Legacy of innovation. Pioneering achievements of the F-100 Super Saber continue to influence modern aviation design and engineering practices. As America's first supersonic fighter, this remarkable aircraft established numerous precedents in aerospace technology, The F-100 Super Saber's development essentially redefined aircraft design parameters. North American Aviation produced 2,294 units across multiple variants, establishing new benchmarks in supersonic flight capabilities. The aircraft's distinctive features included a 45-degree wing sweep configuration, an elliptical nose intake design, advanced titanium integration, and innovative control surface arrangements. Primarily, the F-100D variant demonstrated exceptional versatility. With 1,274 units manufactured, this model's success notably influenced subsequent Century Series fighters, setting standards for supersonic aircraft development. Throughout the 1950s and 1960s, the technical accomplishments of the F-100 program went well beyond its initial design and played a pivotal role in shaping modern aviation. Its engineering milestones demonstrate the aircraft's significance and far-reaching impact. Notably, the F-100 was the first aircraft capable of maintaining supersonic speed in level flight, setting a new benchmark for high-speed performance. In terms of service length, the aircraft remained operational from 1954 until 1971, proving its durability and versatility over nearly 2 decades of use. The F-100 also made a remarkable combat record, with over 360,283 sorties flown during its time in service, showcasing its reliability and effectiveness in diverse mission scenarios. Furthermore, the aircraft's altitude performance was equally impressive, with a service ceiling surpassing 50,000 feet, allowing it to operate in a wide range of operational environments and at extreme altitudes. The Air National Guard's involvement certainly enhanced the aircraft's capabilities. Throughout the 1970s, Air Guard maintainers implemented significant upgrades that resolved persistent engine performance issues. Therefore, their contributions demonstrated the value of operational experience in aircraft development. The legacy of the F-100 Super Saber continues to shape modern aviation, with its development influencing several key aspects of contemporary fighter design. In the realm of structural engineering, the aircraft's design process contributed to the advancement of metallurgy techniques, enabling the use of stronger, lighter materials that have since become standard in military aviation. It also played a role in the evolution of stress distribution analysis, which improved the design of airframes to better withstand the forces encountered during flight, as well as fatigue life prediction methods that extended the operational lifespan of aircraft. In terms of flight control systems, the F-100's innovations in stability augmentation technology laid the groundwork for modern systems that enhance aircraft control, especially during high-speed or turbulent conditions. The integration of control surfaces was another significant advancement, allowing for more precise handling and maneuverability. Additionally, the aircraft's aerodynamic design principles contributed to the ongoing optimization of aerodynamic efficiency, which continues to be a priority in the design of current and future fighter jets. The Super Saber's combat experience shaped tactical aircraft development. Hence, its role in Vietnam, where it served as one of the most effective close air support platforms, influenced future ground attack aircraft design. Air National Guard F-100 units achieved remarkable success in theater operations, thus proving the aircraft's adaptability. The restoration and maintenance practices developed for the F-100 continue to benefit modern aviation. Namely, recent F-100 restoration projects have enabled new generations of fabrication specialists to hone their skills. These efforts ensure that the aircraft's technical legacy persists since restoration techniques often applied to contemporary aircraft maintenance. The F-100's influence on NATO air forces proved substantial, as numerous allied nations adopted the aircraft, whether serving as an air superiority fighter or fighter bomber. The Super Saber demonstrated remarkable versatility. Unless superseded by more advanced aircraft, like the McDonnell Douglas F- for Phantom, it remained the principal tactical fighter of the U.S. Tactical Air Command. The F-100 Super Saber's innovations in weaponry also had a significant impact on the design of future aircraft. The aircraft was capable of carrying up to 6,000 pounds of ordnance, demonstrating its versatility in combat. Its armament included 420mm cannons, providing a powerful means of engaging air and ground targets. Additionally, the F-100 could be equipped with a variety of air-to-air missiles, enhancing its combat capability against enemy aircraft. The aircraft was also designed to carry a range of air-to-ground weapons, enabling it to engage a wide spectrum of targets on the ground. Furthermore, the F-100 had nuclear delivery capabilities, marking it as a crucial asset in strategic missions during the Cold War. This weapons integration experience shaped the development of subsequent multi-role fighters. The F-100's ability to adapt from its initial air superiority role to a fighter-bomber configuration established a precedent for flexible mission capabilities in modern combat aircraft. The F-100 Super Saber marked a crucial moment in aviation history, representing America's first successful supersonic fighter. With innovations like the 45-degree wing sweep, extensive use of titanium, and the powerful J57 engine, it pushed the limits of 1950 aerospace technology. Although it faced early stability issues, the modifications that followed turned the F-100 into a reliable combat platform, influencing future aircraft design. What do you think about the F-100's impact on aviation? Let us know in the comments. If you enjoyed this video, don't forget to like it and subscribe to the channel for more exciting content. Thank you for watching.